cycle. Brayton cycle was proposed by this person in 1870, but initially for reciprocating oil burning engine. But later, this cycle was actually used for rotating machinery, not reciprocating engine. So the engines which we have studied so far, Otto cycle or diesel cycle, both are reciprocating type of engine. But this type of Brayton gas power cycle or gas turbine cycles, those are not reciprocating type of engines. Those are rotary engines. Means compressor is a rotary compressor. Turbine itself is a rotary machinery or device. So here we do not have any reciprocating type of motion. So here is the schematic of gas turbine cycle, which is operating on this cycle, which is called Brayton cycle. We'll see now. So here in this cycle, the first process is compression, right? So the same normal ambient air is first compressed, pressure and temperature is increased. Now it enters into a combustion chamber where fuel is burning with this air, and this high pressure, high temperature gases are entering into a gas turbine, and we get work output from this gas turbine. But some of this work is used to derive compressor, because we need energy to derive compressor. So it means the work output of this turbine must be greater than the work of compressor. So this total W of turbine minus W of compressor is our net work out. Okay. So after doing the work, these gases leaves into the ambient, because we cannot reburn those gases. It's not steam, right? So that is the basic open cycle. It's an open cycle. Air entering, air is leaving, which is used in gas turbines. What is the purpose of a gas turbine? Is to produce electrical energy. So it means there you have a generator. The same gas turbine cycle is also used in jet engines. So in jet engines, what we have after turbine, nozzle. So high pressure, high temperature gases which are leaving the turbine, here you will have a nozzle. So that is coming after this cycle. So we'll be studying jet cycles. So in jet cycle only there will be one more component, and also there is another component at the start, diffuser, and at the end nozzle. Okay. So we only assume that it's no exhaust and yes, that is the actual cycle we have seen. Now we shall apply air standard assumptions, which we already studied, to this cycle. All right. The actual one is like this. Yes, we'll be studying ideal cycle for. Okay, all these points are simple. You can easily read. So here you can see a comparison of gas turbine cycle versus reciprocating type of engine. So here just like intake, then compression, but compressor is a rotary compressor, right? As the fluid is moving through this part, its pressure is increasing, because in the direction of flow, the area is dropping, right? And energy is transferred from this rotor to the fluid to increase its pressure. And of course, temperature will also increase because it is gas. So next, just like here, we have combustion and expansion. Here we have combustion and then expansion in the turbine section. So in the turbine section, now you will see area is increasing. Now it is expanding. Fluid is expanding. So fluid energy is transferred to this shaft. And this shaft is connected to compressor. Okay. And then it is exhausted. But if it is a jet engine, then this exhaust gases will be flowing through a nozzle. Okay. Or otherwise, it is only the work of that turbine is used to derive the generator, and electrical energy is produced. Okay. Okay, it's clear. Now we will apply the air standard assumptions and will make this open cycle a closed cycle. So the same assumptions which we have already studied, we shall apply to this one. So we have replaced combustion chamber with heat exchanger, only heat addition, and yes, the exhaust is replaced with another heat exchanger or heat rejection process. Okay. Now we can show it on PV and TS diagram. Here in Otto cycle, this process was constant volume, but in diesel it was constant pressure. What about here? Is volume constant when the fluid is flowing? No. So here constant pressure assumption is more suitable than constant volume because fluid is continuously moving. In Otto cycle, for a tiny moment, the volume was fixed and heat is released. Right? But here fluid is continuously moving. It's a steady flow process. Same here. It's not like Otto cycle or diesel cycle. Here the fluid goes into the ambient, to the ambient pressure, and at the same pressure it is entering. So what is happening in the ambient, only heat is released to this constant pressure ambient. So this process is also constant pressure heat rejection, constant pressure heat addition. In Otto, one was constant volume, other was constant, both were constant volume. In diesel, it was constant pressure and constant volume. In Carnot, isothermal. So let's quickly draw its PV and TS diagram. PV, TS. So TS is simple, 1 to 2, isentropic. Compression, 2 to 3. Constant pressure, isobaric, so constant pressure line. Heat addition, another isentropic, workout, and then another isobaric, heat rejected. Okay, here is work in for compression. TS, now PV 1 to 2, isentropic means PV to the power K is equal to constant, 1 to 2, 2 to 3, constant pressure, heat addition, another isentropic expansion, PV to the power K is equal to constant, and isobaric, another constant pressure heat addition, Q out. And this is representing your dead state, in other words. So you see in every cycle, first we increase the pressure and temperature higher than the dead state. Then we get work and we come back to dead state. In every cycle, we start from the dead state, we increase the pressure, temperature, gets the work out, and we again at the dead state. So the purpose of every heat engine cycle is to increase the pressure and temperature from the dead state to higher one, and then again comes back to the dead state, but by extracting some useful work from that system. Okay, time is already finished. So these are the two lines, TS, PV. So the next we. So let's start it. Okay. So last time I think we covered the basic theory of Brayton cycle, the basic working principle, and then we also discussed the air standard assumptions. If we apply to this Brayton cycle, then this cycle looks like this, where combustion is replaced with heat exchanger, and exhaust is also replaced with another heat exchanger. And both of these processes or heat exchange processes are now constant pressure, right? Compression and expansion is, as usual, will be isentropic and isentropic for ideal cycle. Now we shall derive its efficiency. We know efficiency, the general equation, efficiency is equal to 1 minus Q out over Q in, or W net out over Q in. So what is Q out? Here H4 minus H1 because it's a constant pressure process. Similarly, here we have H3 minus H2 because we are dealing with ideal gas, so we can replace it Cp into T4 minus T1 divided by Cp into T3 minus T2. So here we are still assuming constant specific heats for ideal cycle, so this will cancel. So now again, just like in Otto cycle or diesel cycle, we have efficiency in terms of temperatures, which we do not like. We want to convert it into a form which we can easily interpret. Okay, so that is the efficiency equation. So now we'll do some mathematical manipulations so that it can be transformed into a form which we can easily study. In case of Otto and diesel cycles, you had here compression ratios, okay, which we define as R. In case of diesel engine, we have R and RC cutoff ratio. Both were volume ratios. But here we'll have pressure ratio, RP, P2 over P1 or P4 over pressure ratio in terms of pressure ratios, because the cycle is different. It's a steady flow process. There are no constant volume processes because there was a piston cylinder mechanism. Here it's a continuous flow process. Okay, so now let's do it here. Or okay, if I explain right here, if we take T1 out, T2 out from here, why T1 over T2 is what? Isentropic process. And for isentropic process, we know PR, P1 over P2 to the power K minus 1 over K. If it is isentropic, ideal gas and constant specific heat. Okay, so it means, and this one I'm representing this term, now we are defining a new term as pressure ratio. Pressure which is increased inside compressor. P2 over P1. So this term can be written as 1 over Rp to the power K minus 1 over K. So it means if I take T1 out, T2 out, so here I will have T4 over T1, this is 1, and here I will have T3 over T2. So this T1 over T2 can be replaced with this term in terms of pressure ratio. Now what is left here? T4 over T1 and T3 over T2. So what we can do with this one? Again, go to isentropic processes. Isentropic processes, T2 by T1 is equal to P2 by P1 minus 1 over K. P2 is equal to P3 pressure during heating, and P1 is equal to P4. So it means this term is equal to this term. And 3 to 4 processes, isentropic. So the same can be written as T3 over T4. Okay. So we have proved that this term is equal to this term. Yeah. So if you cross multiply, so it will show us T4 over T1. T4 over T1 is equal to T3 over T2. That's what we want. A very similar expression which we obtained in Otto cycle. So it means this these two are equal. We have proved it, so this term will cancel. So efficiency is only 1 minus efficiency of this ideal Otto cycle is now represented in a very simple expression. It is very similar to Otto 1 minus 1 over R compression ratio. It was there. Here it is pressure ratio. And of course, this term is also different. Here it used to be K minus 1. Here it is K minus 1 over K. Okay. Any question? So this is done here on this slide already. Q in, Q out, efficiency. Here again, the major assumption is we are assuming constant specific heat. So this is clear. Efficiency is as a function of pressure ratio and specific heat ratio. Any question from here?
Here we also don't consider intake and exhaust.
Yes, here intake and exhaust actually has nothing to do. In auto and diesel, there is a complete stroke. Here intake is nothing. Intake is just the start of compression. Intake is coming from the air, ambient air, and it enters into a compressor directly. In auto and diesel, there was a complete intake stroke and exhaust stroke. Here we have.
I'm referring to what happens in the combustion chamber.
Combustion chamber is this one, 2 to 3. Okay, because their schematic is not here, so let me draw schematic. Compressor, combustion chamber, turbine, and this exhaust. Compressor. 1, 2, 3.
Combustion refers to the release of carbon dioxide.
Yeah.
But here it's mentioned that the working fluid is only air. So how carbon dioxide is produced in the combustion chamber where there is no the required substances don't exist.
Yep. The first lecture of this chapter, when we discussed air standard assumptions, remember?
I remember,
Yes.
yes.
So when we said air standard assumptions, so here it is air entering, air fuel. How much fuel we have to supply? We'll see in next chapter. To burn 1 kilogram of fuel, of these fuels, normally auto, diesel, or jet fuels, or natural gas, to burn 1 kilogram of fuel, we need about 15 to 30. In here, we will see up to 50. We will see now kilograms of air.
So my question: does combustion happen?
Yes, combustion has happened.
CO2 is released.
CO2 is released, right? How much CO2 compared to nitrogen? Nitrogen did not react. So major part is still nitrogen. And this whole mixture is behaving like air. Its properties are very similar to air. That's why we assume throughout air for air standard assumptions. That is for elementary thermodynamics. That's what we do. Actual analysis is very, very complex. And for that, we have computer simulations now. Because there are so many substances. For every substance, there is internal energy, enthalpy, everything is changing. That's mixture of gases we have to treat. That is another chapter in the same book, chapter 15, 14, mixture of gases. So, yes.
Their standard assumptions for approximation.
Yes.
How much is the difference between actual and standard?
Okay. See the previous lecture videos when we saw this compression ratio versus efficiency versus compression ratio. I told you this is for ideal, for gamma is equal to 1.4. So real one would be around here, about 20 to 30. If you so now this is the efficiency under cold air standard assumptions, which we are. Now we can see the effect just like for Otto and diesel for different pressure ratios starting from 1. 1 means P2 over P1 is equal to 1. So of course P2 will be higher than 1. So it will be at least starting from 2 onwards. Okay. So you will get such for this gas turbine cycles. So it's not compression ratio, here it is pressure ratio. What is pressure ratio? The pressure which is increased inside the compressor. Look here, if I increase this pressure from 2 to here, this point 2 is shifted here. Now there will be combustion. So point 3 is also shifted here. And then for the same, this is ambient. For the same ambient, if you keep on increasing this pressure ratio, your network area is increasing. That's what this graph is telling us. Okay. But there is one issue. If you keep on increasing this compression ratio, where is this 0.3 is ending up? Increasing. So those materials, can they sustain such high temperatures? That is the issue. Yeah, by increasing compression ratio, efficiency is increasing, but at the same time, now you have to see where is 0.3 going.
Compressing the air is not so much work.
Yes, and this work is coming from the same turbine. So a major portion is also going there. So this curve is not, this curve is for only for ideal cycle where you have no restriction on 0.3. For example, maximum temperature which materials can sustain, the current materials which are used in these gas turbine engines, that is about 1000 Kelvin normally. So if this is 1000 Kelvin line, 1000 Kelvin temperature line. So it means if this is 1000, so if you are crossing, so you do not have materials which can sustain such high temperatures. So now you have to see this effect of pressure ratio by fixing T3, maximum temperature. Now if you analyze, if you fix T3, that you cannot go beyond this line, then now let's do it again. The effect of pressure ratio by fixing T3 and T1. This is ambient, that is not in your control, that is ambient temperature. Okay. And P naught, of course. So now let me redraw it again. This is the maximum. Okay. So if I increase this 0.2 to here, I can end up maximum here. Now this is the new curve. So it looks like efficiency is increased. Network area seems compared to this one has increased because this is the new area. If you further increase, but I cannot cross this point, so I will end up here. So maybe again area is further increased, but for very high pressure ratio, for example here, now the area seems to be dropped. So by fixing T1 and T maximum, and if you now keep on increasing the pressure ratio, the curve will not be like this. The curve will be, it will increase, it will reach a maximum, then it will start to drop. RP versus efficiency. By keeping T3 and T1 fixed, means T maximum and T minimum. For a given T maximum, T minimum, by increasing pressure ratio, it will not keep on increasing. So this curve is valid when there is no restriction on T3. When there is a restriction on T3, then because now a large amount of turbine work is going back to derive compressor. Okay. That's what is explained in the next diagram. Okay. So we can derive it, that what is that pressure ratio? What is that pressure ratio for a given T maximum and T minimum, which will give us maximum efficiency. So if you derive that, will be the end answer. So for a given T maximum and T minimum, this should be the pressure ratio, which will give us maximum efficiency. Okay. So it means there are three things which we have to take into account: pressure ratio, how much pressure ratio we can rise. At the same time, we have to keep T3, and also the net work output. So there should be a compromise between the pressure ratio, and of course it is affecting thermal efficiency, and the net work output. Okay, if you want to get maximum efficiency, for example, this gives us maximum efficiency. If you further increase pressure ratio, we get lower efficiency. Okay, so it means this is the maximum I can get from what? For fixed temperatures. And on these diagrams, on TS, PV, or any other diagram, what we show? Temperature versus, what is this entropy? What are the units? Per kilogram, per. So everything which we are showing here, it is actually for 1 kilogram of a substance. From 1 kilogram of that working substance, I can get this much maximum.
Can you repeat the relationship between Emax and the previous graph of the how it affects the efficiency?
Okay.
How it restricts it?
Okay. So for example, if your pressure ratio in the compressor is this one, very small pressure ratio, then this whole heat you supply in the combustion chamber to reach the maximum temperature which we want, and then there is expansion in the turbine. Okay, and then it is exhausted, and this exhaust we have replaced with heat rejection process. Okay, so this is the net work done I can get. If I increase the pressure ratio to here, you cannot, that's why we stop here. Okay, and then there is expansion to the same ambient pressure, that is the ambient pressure below which we cannot go. Okay, but temperature is still higher, exhaust gases, and that's why it is going into the ambient. So now from here to here, maybe net work area is increased compared to heat supply, so it's fine. But if you increase this pressure ratio to a very large value, okay, then of course you are supplying very less heat, but whatever work you are producing, the major part is going back to derive that compressor. That's why this area may be now smaller than this one, becomes smaller than this one. So by increasing the pressure ratio, efficiency keeps on increasing up to a certain point, and then it will start to drop. If this is fixed, if you cannot cross this line.
Or what about intermediate cooling and compression?
That is coming later on. First, we are discussing the basic cycle. Now, how to improve the efficiency of this basic cycle, those are the other ways how we can improve the efficiency. Like in auto and diesel engine, we did not discuss many things. How to improve the efficiency of auto engine, we use turbocharger, supercharger. There are other ways. Okay, so is it clear somehow? Okay. Okay, what I was saying, I was telling you that everything which we represent on these diagrams, those are for 1 kilogram of mass. So it means from 1 kilogram of mass, that is the maximum work I can get from 1 kilogram. So for example, you want to design this power plant to produce, for example, 1000 kilowatts. Okay, so you know what is T minimum, what is T maximum, and you choose certain pressure ratio which will give you maximum output from 1 kilogram. So you calculated this W, small w, and it comes out to be 4 kilojoules per. That is what you can get maximum from 1 kilogram. To get this much, what should be done? Multiplied with that m dot, which can give me this power. Right? So here everything is for 1 kilogram. So then you multiply with the m dot to get the required power, which is our requirement. Okay, so for 1 kilogram, that is maximum possible. So now you have to multiply with that m dot. What will be the size of your compressor? That will be defined by this m dot into this, not just 1 kilogram. That is only for 1 kilogram, which we are showing up here. Multiplied by m dot. Now your compressor will be designed, turbine will be designed. So now in these systems, because major power is going back to derive compressor, and the network output you cannot compromise here, so you will keep on increasing m dot until you get the required net power output. Okay, so that will be discussed.
So in the auto cycle, the V1 always will be the V of the atmospheric condition, and not at T.
Yes, at which the
So how we can determine the size of the engine? It depends on the mass which it will enter to the piston cylinder.
into the piston. After that, what is happening? Compression and then expansion. That is the volume which has gone into the system. Now you are compressing it, and then you are getting the power from that mass. That comes later, because atmosphere is not under your control. So whatever is there, now you will increase the pressure and temperature from that.
No, I'm saying that how we can determine the size of the engine.
What is your power requirement? First, that's what you should know.
Okay.
And then you will you will do the analysis for 1 kilogram. If 1 kilogram of mass is entering, then this will be the volume. Can it give me the required power? No. So either increase the mass or increase the size of the engine. Right? For example, for size, you have a restriction. Engine size cannot be bigger than this space. So it means total volume is fixed. When total volume is fixed, now what you can do? Increase the mass flow rate to get the desired power. Okay.
Is there a problem for adding heat necessary?
Yes, more fuel has to be supplied. When there is more m dots, okay, let me explain this thing. It is coming in again, so I will explain it. So let's finish this thing. So if you are getting very less network output from 1 kilogram, so it means you have to increase the mass flow rate. So your system is dealing with a large m dot. So the compressor power is not just delta H, it is multiplied by m dot. That is the total compressor power or total turbine power. Okay. So delta is just for 1 kilogram multiplied by m dot. These are the pressure ratios which are normally used in these gas turbines, 11 to 16. Air in this gas turbine. In your auto engine and diesel engine, there is a cooling mechanism, because during combustion temperatures are increased to very high. So that's why we need cooling of the walls of the engines. And for that, what we have in auto and diesel cycles, there is a separate cooling system. Cooling water is flowing. Here, there is no cooling water flow. There is no separate cooling system. And here also, the temperatures can increase to very high, for example, 1000 Kelvin, maybe actual temperature which rises more than this when immediately fuel burns. We'll see in the next class, in the next chapter, the temperatures when you burn a particular fuel, what is the maximum possible temperature we can obtain. So that will be around 2000 plus if you burn petrol or diesel or these fuels, and every heat is contained there, as if it is not lost, then maximum temperature which can obtain, it will be higher than 2000. So that's why cooling is definite, because your materials of construction cannot sustain such high temperatures. So here what we do for cooling. Look here, to combust this fuel, I need 14 kilograms, for example, or 20 kilograms to burn 1 kilogram of the normally fuels which are used here in gas turbines are a natural gas or another liquid fuel. I don't forgetting the name. It's not petrol or diesel, another liquid fuel or natural gas. Natural gas is commonly used in these. So to burn this 1 kilogram of fuel, you need 20 kilograms of air, minimum, for example. But you will supply here 50 kilograms. So what will happen? 20 kilograms will react with fuel to burn. What is the purpose of the remaining 30? Some of the heat will be absorbed by this air, which is not taking part in the combustion, but it is still there, present there. So it means it will absorb some of heat in it, because by burning this fuel, temperature was increased to 2000, but it will immediately reduce because there is a cooled air there, much cooler air, which is not reacting with fuel. So in these engines, air performs two functions. One, of course, to burn the fuel. Second, it acts as a coolant itself. Okay. So air fuel ratio of 50 or above is not uncommon. Look, only 20 kilograms was required to burn 1 kilo, but we are supplying 50 kilograms. So the assumption, air standard assumption, is more valid here than auto and diesel. It's more valid here. Okay. So that assumption, if you do not like this assumption, it's more valid here. Because you are supplying much larger air than required. Not in auto and diesel. There we supply the same amount which is normally required to burn. Okay, because we have a separate cooling mechanism there. Okay. So that's why treating the combustion gases as air does not cause any large errors. What are the applications of these gas turbines? Of course, for aircraft and to produce power. These are the two major applications of these gas turbine engines. In these engines now, the major portion of this turbine work, where it is going. The work produced by this turbine, major part is reused here. Because this turbine is mounted on the same shaft as with the compressor. So the net work output will be quite small compared to the total work which is produced by this turbine. Why? Now let's compare it with steam power plant. Here, turbine is also supplying work to pump. Yeah, so it's liquid here. Here it's air. So here PdV and here PdV, because this change in volume is negligible here. Here change in volume is not negligible, not at all. That's why this work of compressor is significant in these gas turbines. If you compare a gas turbine versus a steam power plant, that is the major disadvantage of these gas turbine engines. A major work is reused, power is reused to derive the compressor here. But here you do not have any condenser, just air entering, leaving. Here you have a huge condensers, a cooling mechanism. So initial cost is much larger here because this is a huge component. It's not just simple condenser. Here you have a cooling water. This cooling water is going where? Have you seen such cooling towers? You would have seen such cooling towers. So this water is going here. Here you have fans. It is taking the normal air. That is called evaporative cooling going on. So this water takes heat. Now it rejects this heat to this air, normal ambient air. It cools down and comes back. So that is a huge investment you have to make in steam power plants. Why you are converting gas into liquid? So that this power is negligible. So that's why when you want to decide which power plant is best for your site, so that's what you have to take into account. A complete economic analysis has to be performed. This is the high initial cost, and also the maintenance cost is much higher because here everywhere it's water, corrosion, etc. in these engines. But the major disadvantage is this one. The work output of turbine and the back work ratio is negligibly small here.
When the work of compressor, the work of pump will equal to the work of condenser. Because compressor requires fixed power.
Yes, pump also required.
But if I add them both, it's equal to the compressor for the
Okay, do not compare like this. For example, here you have a 50 megawatt gas power plant versus 50 megawatt steam power plant. Okay, here to get this 50 megawatt, the turbine is producing 150 megawatts because the remaining 100 is reused. Here 50 megawatt, the part which is reused here is only 0.1 maybe. No, for the condenser what you need, it's all liquid. Yeah, there is a fan, but still this will be much smaller than if we do that detailed analysis. That's why I'm telling you, yes, initial cost is much higher. There is a fan, but now you need to compare how much power this fan is required, because fan is not compressing anything. It is only making the air to flow. So the power of the fan will be much larger compared to when you are compressing something. You need much more power. Fan does not compress air. It's only mobilize the air. That's all. Okay, so that's the main thing. Back work ratio in these power plants are much higher compared to steam power plants. Okay. So back work ratio is defined as work of compressor divided by work of turbine. There is another term which is called work ratio, that is back work ratio. Work ratio is net work output divided by turbine work, total turbine work. So there's two different ways to define the same thing: back work ratio and work ratio. Okay. So that's why if you see two equal capacity steam power plant and gas power plant, both are 50 megawatts, which turbine will be larger in size? This one, definitely. Size of these components will be, because they are handling a huge amount of air throughout. Yes, but they have to produce much larger power because major part is reused. Gas power plants. So let's come back to the cycle. The ideal cycle, but actually everything is not ideal. Every process has irreversibilities. Like in compressor, we already know isentropic. This is non-isentropic. Similarly, turbine isentropic, non-isentropic. There is also a pressure drop during heat addition. There is also pressure drop during heat rejection when the fluid is flowing through combustion chamber or when the fluid is cooling down. So there will be such pressure drops. But normally we neglect these two effects, but we do not neglect these two. So if we do not want to neglect the non-isentropic effects here and here, then we define a term which is called, if you remember from previous chapters, isentropic efficiency. When we say this process is isentropic, means isentropic efficiency is 1. If I say isentropic efficiency is 0.8 or 0.9, so it means the remaining 10% are representing the irreversible losses. So we can account for these irreversible factors by defining isentropic efficiency of compressor. You should remember what was this? Isentropic divided by actual. And similarly for turbine, actual over isentropic. Okay, so now let's do a problem of this simple power plant, Brayton cycle. This will come again in the course of power plants. This gas power plant, you will do it again. Here we are only solving the basic cycle. Okay, there are many versions which we will study. Only theory, numerical problems you will do in that power plant course. Okay, a gas turbine unit has a pressure ratio of 10 to 1. So first let's show its schematic. Compressor, combustion chamber, turbine, going into the exhaust, and this exhaust we will replace it with heat rejection. And turbine is connected to a shaft, to a compressor by a shaft. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Let's show it as heat rejection. Okay. Also show it on TS diagram. PV we normally do not use for these diagrams. TS is better. PV because cylinder piston mechanism, where you have those reciprocating type of engines, PV gives you much better imagination about what is happening. Here TS is enough. 1 to 2, 2 to 3, 3 to 4, 4 to 1, constant pressure, okay. So isentropic compression and isentropic expansion. Yeah, to not do it in exam. Yes, I will deduct marks for this one if arrows are reversed. Okay. A gas turbine unit has a pressure ratio of 10 to 1. So what is given? Tell me, P3 over P2 or what? P2 over P1 is given as 10 over 1. Okay, pressure ratio is 1. And maximum cycle temperature, which one? 3. 700 degrees Celsius plus 273. So it's almost nearing 1000 Kelvin. Okay. The isentropic efficiencies are given for compressor and turbine. So it means you cannot assume isentropic. It will be actual 2A and let's use 2S for compressor and similarly for turbine. 3 to 4A, 4S. Okay. Chapter 2. Everything, the whole thermo is actually being repeated Okay. So isentropic efficiency of compressor, isentropic efficiency of turbines are given, and those are not 1. They are less than 1. So what is given? Isentropic efficiency of compressor means what is given? 0.82 is equal to H2S minus H1. That is given. And here we are dealing with air. Okay, so I can write it as Cp, because in this entire chapter we have not used steam tables. We'll do it next chapter in combustion, after combustion. So far in this chapter, no steam tables. Okay, so I will be giving steam tables in the exam. So let's see how many students remember. For this chapter, no steam table is required. So Cp into T2S minus T1. So I will be giving steam tables for calculating H1, H2. Some students will say, "Oh, that is exactly given. I do not need to interpolate." But here it's not steam table; it's air. Okay. So if it is constant, that is given for compressor. What about turbine? Turbine isentropic efficiency is also given. So H3 minus H4 A actual over 4S. Okay, so again you can write it in terms of temperatures. Cp into T3 minus T4A over Cp into T3 minus T4S. Let's read. Maybe he's saying that variation of specific heat has to be taken into account. Then you cannot cancel it like this. Okay. Calculate the power output of this electric generator, which is geared to the turbine, when the air enters the compressor at 15 degrees Celsius, T1. So this is 15 degrees Celsius. Ambient air. Okay. At a rate of, so there is m dot, which is flowing in this cycle, is 15 kilograms per second. Look here, take Cp and gamma for the compression process. For the compression, Cp and gamma are given, and Cp and gamma for expansion separate, two different values. So Cp and gamma for 3 to 4 are different from 1 to 2. Here it's pure air. Here you have mixture of gases. So he is saying assume take different value of Cp. So you will still assume constant specific heats, but different for different processes. For compression, Cp of pure air and gamma of pure air. But for expansion, Cp is a little different, higher. It's more heavier gases. It needs more energy to change its temperature, and lower K, Cp and Cv, 1.33. This mixture of gases. And what about combustion? Because combustion is starting from pure air to mixture. So he's saying that use this one for expansion. The same Cp should be used for combustion process. Okay, so it means it's a constant specific heat problem. But we are using two different specific heats, so the error will be less. What we need to find out: power output, efficiency, and back work ratio. So power output, can be written as net power output, work of turbine minus work of compressor, or Q in minus Q out. What is work of turbine? H higher minus H3 minus H4 minus work of compressor H2. Now you must write A, and H2A minus H1. Okay. No steam tables, it's air. So m dot Cp into T3 minus T4A. M dot, you can take common, Cp is common. For the compression process, same Cp. So T2A minus T1. No, for turbine it's different. For yes, it's different. Cp for turbine, Cp for compressor. M dot is same. Okay. At least I have learned this now. To the use of brackets. Okay. So that is power output. So what we need to calculate? All the temperatures. CPs are given for turbine and for compressor. It's clear? T1 initial temperature we know, final temperature is also given, so we need to calculate T2A and T4A. So how we can calculate?
We have to find the asymptote. We have to find the asymptote.
Yeah.
And then
We can find out this T2A with the help of T2S. So for isentropic process, because we have this equation, I can find T2A if I know T2S, and T2S for isentropic, for ideal gas, and for constant specific heat. So look at the usefulness of these equations. T2S over T1 is equal to T2 over P1 to the power K minus 1 over K. So find out T2S from Kelvin. Pressure ratio is given 10 to 1. That's what you have decided. So this should be the pressure ratio.
and what is
Here it's air, pure air. 1.4. Here it's given, take 1.33. 1.4 for compression. So first,
It's K2. You can say K1, K2.
okay. So for this process, this is K1, for other is K2. Okay. So find out T2S first, then put it here to find out T2A. Same you will do for isentropic expansion. T3 over T, I want to find out T4, so let's write it. T4S isentropic. T3 is equal to P4 over P3, which is same as this one, to the power K2 minus 1 over K2. Okay. Expansion process. So find out T4S, T3 is given. This ratio is same as this one, so put it here. T4S and find out T4A. That's what we need here to calculate power. So once all temperatures are known, put it here to find out the power output. Next is to calculate efficiency. Efficiency is the same net power output. W dot net out divided by Qn. So what is Qn? M dot Cp. For combustion process, use this Cp. T3 minus T2A. So already you have calculated temperatures, just put it here to find out Qn. Okay. Yes, actual points. Isentropic is only used to calculate actual ones. the usefulness of this concept isentropic.
And how to find if I don't have
If you do not have this one, look, what you are saying in compressor, you are saying maximum irreversibilities or friction losses should not be, so you are assuming a good compressor should not have more than 20% losses. Okay. So that makes your calculation much easier. Okay. That's why I told you this concept of isentropic is so important. This entropy and isentropic, this makes our design much easier. Back work ratio. Okay, any question? Ask. Because the proper solution is already there. Here I'm just trying to explain and try to understand. Okay, let's go through the solution quickly. That's what you are required to do in the exam. Draw the schematic with complete labeling. Maybe 4 or 5 marks for this one, 4 or 5 marks for this one, and then the solution. Back work ratio is how we defined it. Work of compressor divided by, what is work of compressor? M dot Cp T2A minus T1. Work of turbine T3 minus T4. So it's very simple. So just quickly go through the solution. These are, now let's see the values. Work of turbine, only work of turbine is this much per kilogram is written here, 401. And what is work of compressor? So you can see a major part is reused here. So what is the net work output is very small, only 73 out of those 400, only 73 is the net work output. So multiplied by m dot will give me the power. How much power this gas turbine power plant can make? Almost 1100 kilowatts. The actual net work output. Okay. And then we can find out efficiency, network output divided by the heat supplied, process 2 to 3. So only 18.4% is the efficiency of this basic air Brayton cycle. Okay. Ask any question. Okay. Okay. So the back work ratio. The work, the portion of work going back to the compressor. So it's 82%. What's your name? Hassan. Which one? It's alphabetically. This one? Still have time. So that is back work ratio, work ratio. Total network output of the turbine divided by total work of turbine. So the same thing in two different ways is written. Okay, so you can see the efficiency of this. These engines are very less, even with some assumptions. Right. So how to improve the efficiency? So there are different ways to improve the efficiency of this simple cycle. So we'll just go through the basic theory of improving the efficiency. The numerical problems related to that one you will do in power plants. Okay. So what are the ways to increase the efficiency? One of the ways is this one. Look, when it leaves the turbine, its temperature is still very high. Pressure is same, but still temperature is higher than ambient. If this temperature is higher than this one, if it's not here in this problem, the difference between this 0.4 and 2 is very small in this problem. But if you have a significant temperature, if I redraw it like this one, this is compression, heat addition, turbine. If this 0.4 and this 0.2, T2 and T4, if you have a significant temperature difference available, so what we can do? Use it here by using a heat exchanger. Preheat this air which is entering into the combustion chamber. Because this was the exhaust, its temperature is still higher than this temperature. So use it to transfer heat here without any fuel. The same fuel which you burnt here, and you get the work output, right? Now when it is leaving, its temperature is still higher than this one, then reuse it as a fuel. Actually the same, it was the exhaust, but we are reusing it to preheat. So now you have to supply less heat, in other words. So it will increase the efficiency. This is a heat engine. We are increasing the efficiency of this heat engine. It is already a heat engine.
By adding another
Another exhaust.
Add the 0.4 exhaust.
Yeah. Put another engine.
I see.
Yes, we do it. You will see in steam power plants, we can use this, that is called combined cycle power plant. This is gas power plant. If this temperature, for example, here the temperature is 1000 Kelvin. Now after doing this work, this temperature is 400 Kelvin, for example. Now I can use this one as a boiler for steam power plant. You can boil the water, because for boiling water you need temperature less than 400 Kelvin. Yes, that is called combined cycle power plant. Here you have gas power plant, here you have steam power plant, and boiler is taking heat from the exhaust, and that is done. Okay, so this is something you will do in power plants. You will see. This is called combined cycle power plant.
Can we add another turbine?
Yes, that's we will discuss now. Okay, so in the next class we'll discuss how we can increase the efficiency of this engine. Okay, one of the ways is this one. Now we'll discuss in detail how it can increase the efficiency and what are the limits, etc. Okay, in the next class.